Hi all, my name is Julieta Granados. I'm a first-year PhD student at Rice University. I'm part of the Campeonatos lab in the Electrical and Computer Engineering department. My job is to develop wearable biosensors for health monitoring. You may wonder, why do we need wearable sensors? Let me give you an example. Did you know that people with diabetes need to constantly check their blood sugar levels? As you can see in the video, this involves pricking their fingers with a lancet and measuring the glucose levels with a device called a glucometer. Now imagine doing that several times a day. What if you could monitor whatever molecule is present in your blood, but without needles or without pain? What if you could track health in biofluids like sweat, saliva, and tears? In our laboratory, we develop wearable sensors to monitor analytes in non-invasive biofluids. We can measure glucose, lactate, uric acid, hormones, vitamins, alcohol, and many more analytes. To measure these molecules, we use electrochemical sensing techniques. First, we need to determine the target analyte to measure, in which biofluid we want to measure it, and with which biorecognition element we are going to trap the target. We then place the sensor in the biofluid. If the target molecule is present there, the biorecognition element and the analyte will bind. This binding event will induce a change in the electrochemical signal being measured. The change in the signal can then be correlated with the amount of analyte that was present in the sample. In our sensors, we integrate microfluidics to control the small sample volumes. These channels allow us to collect the target biofluid and refresh the sample for new electrochemical measurements. On the same patch, we can also integrate the electronics for signal acquisition and data transmission. If we are using sweat as our biofluid, we can also integrate a sweat stimulation module. And how do we fabricate these wearable biosensors? For sensor fabrication, we use flexible substrates with properties similar to those of the skin. This ensures the sensor can stick to the skin and allow for continuous measurement of analytes. In the figures, you can see examples of wearable platforms we have developed. First, we use inkjet printing of silver and carbon onto flexible substrates for the creation of the electrodes. Then, we deposit Prussian blue, which allows us to obtain an electrochemical signal from the binding event. For applications that need continuous measurement, we use a sacrificial layer of material similar to Prussian blue. The last two steps involve functionalizing the electrodes with the biorecognition element of choice. In this case, we use enzymes. Lastly, we assemble the microfluidics. I am going to run you through the testing protocol for our glucose biosensor. First, we measure the volunteer's fasting blood sugar using a glucometer. This measurement is going to act as a reference for the sweat glucose measurements we're going to perform later. Then, we stimulate sweat on the volunteer's arm through iontophoresis. This process involves placing two electrodes on the skin and hydrogels loaded with a sweat-stimulating drug, which will be delivered into the skin by a small current that is going to flow between the two electrodes. We then attach the sensor to the volunteer's arm and start measuring the current from the sensor. Then, the volunteer eats a sugary meal. After approximately 20 minutes, we will see a change in the signal due to an increase in sweat and blood glucose. At this time, we take another blood glucose sample for comparison between blood and sweat glucose levels. After the test has been completed, we can analyze the data from sweat and blood glucose to determine if our sensor works correctly. Now you may wonder, what are the applications of this technology? The use cases are endless, but I'm especially interested in monitoring women's health. Hormones are crucial for women's health monitoring and management, since they regulate most biological processes from menstruation, pregnancy, and menopause. Hormones are crucial, but current hormone monitoring techniques rely on laboratory tests that are expensive, time-consuming, and invasive. But what if we could track hormones in sweat? We propose the development of a wearable biosensor for luteinizing hormone monitoring, one of the most important sex hormones in women. We propose a simultaneous tracking of glucose and lactates because we hypothesize there is a correlation between the fluctuations in hormones and metabolites that could uncover biomarker signatures that can help diagnose and manage endocrine disorders. Furthermore, we envision our project being a collaborative space with clinicians and patients.